Open the VW 12.1. For our first example, notice how it says an inconsistent system. This word inconsistent is simply kind of a formal way of saying a system with no solution. So underneath it says find the value of A that makes the system inconsistent, meaning no solution. So you might recall from Algebra 1, a system with no solution graphically, all that means is you have two lines and they don't intersect. So something like this. So think of it as the lines are parallel. Meaning same slope, different y-intercept. So for this question, there are lots of ways of doing it. The simplest way to approach any question like this would be to do this. Make your equations match. By making them match, you're basically going to force the slope to be the same. So imagine I multiply this one by 2. The bottom one, let's leave it. So this will be 4x plus 2y equals 10. Then 4x plus ay equals 8. We're just going to compare right here. So our conclusion is a must be 2. And that's it. Let's try the next one. Solving a system of dependent equations. So this word dependent right here, that's another way of stating infinite solutions. So graphically, what that would mean is your two lines are overlapping. So imagine one line here, another line like right there. Lines overlap. Algebraically, that would mean the slope and y-intercepts are the same. So if we go to our first question here, find the value of A that makes the system dependent or infinite solutions, then express infinite solution in terms of x. Don't worry about this part, we'll do that part last. For the first part, find the value of A, we'll do the same thing. Let's make the equations match. So I'm going to multiply this one by -3. So that would be negative 6x minus 3y equals -12, and leave the second equation alone. Remember, we're trying to make them match, so just look right here. And I can see that A must equal -6, and we're done. Now, the infinite solution part in terms of x, that's where it gets a little more complicated. We understand a solution as x comma y. Now, in terms of x would mean we don't want to have a y in our solution. So what you do is you grab this original equation right here, this 2x plus y equals 4. I could have grabbed the other one too, once I plug in -6, since they're the same equation. I just solve for y. So y equals -2x plus 4. And now what I'm going to do is take this thing and plug it in right there. So our infinite solution in terms of x is x comma -2x plus 4. So for example, some solutions would be, let's say I plug in 0, 0, 4 is a solution. I could plug in 1, and 1, 2 would be a solution. I could plug in 2, and 0 would be a solution, and this continues forever. So that's what it means to have an infinite solution, something like that. Now here's the last example. Now we're going to do a system with 3 equations. And the best way to do this is going to be to use elimination. So that's why in the instructions it actually tells you use elimination. I'm going to show the complete work here, What I want all of you to do is to label each equation like this: E1, E2, E3. This will help you keep your work organized and also helps me grade your work because it'll be easier for me to track down your mistakes if you make any. The first thing you want to do is you want to pick a variable to eliminate. So eliminate one variable. Now it could be any variable, doesn't really matter. I like to pick Z just because I like working with X and Y at the end, but you can pick anything, whatever looks easy. So for the sake of the example, I'll pick Z, also because these numbers look easy to work with. So I'll put a note, Z. What I want to do is do 2 times E1, and I'm going to add that to E2. Now, let's look at what that does. If I do 2 times E1, that means 2 times entire first equation. That'd be 2x plus 2y minus 2z equals -2. And I leave E2 alone, because look what happens. E2 is just 4x minus 3y plus 2z equals 16. By leaving E2 alone, I'll notice that these will cancel when I add them. So that's why this line's important, because this is like your instructions to your computer. So we're going to cross those out. Then that would be 6x minus y equals 14. We'll call this one E4. Step 1 done. Now step 2, this is important. You eliminate the same variable with a different pair of equations. That is super, super important. So if you pick Z here, that means you gotta do Z again. You pick X, gotta do X again. I pick Z, so I'm gonna pick equations 1 and 3 to work with. And you can use any pair as long as it's not E1 and E2 again. So for E1 and E3, if I want to cancel out Z, there are lots of ways to do it. The easiest way in my mind would be to multiply E1 by -3 and then leave E3 alone. Because -3 times E1, that would be -3x minus 3y plus 3z would equal 3. And then leave E3 alone. That's 2x minus 2y minus 3z would equal 5. Let's add them. -x minus 5y is equal to 8. Let's call this thing E5. Now by doing that, look at what we just created. You have E4 and E5, and that's just a regular system. So for step 3, you just use E4 and E5 to solve. That's always your goal. Whenever you have a 3-variable system, you're trying to get rid of one of them to get to a simpler system like this. So looking at this, let's follow our same patterns. I'm going to multiply E5 by 6, so I'm going to write E4 plus 6E5. So E4 rewrite. And then 6E5, that would be -6x minus 30y. That would equal 48. Let's add that. So now I have -31y. That's equal to 62. Y is equal to -2. You got y. Once you have y, plug it back into any of these. So if I plug in y to this one, for example, I can see that x should be 2. And then you plug in these two into really any one of these. Probably E1 will be the easiest. So plug those back in, and then we're going to get z is equal to 1. And that's our answer right there. And oftentimes we're going to write that as an ordered triple instead of an ordered pair. So just think, write it in order. 2, -2, 1. So now what we're going to do is put this answer into context. So if you look at these three equations, what's happening is this is in 3 dimensions. So imagine 3 planes like this. Plane 1, plane 2, and then plane 3 can be something like this. The point where these planes meet, so this picture, let's say it's like right here. The point where every single plane touches, that is the solution. So that's what we're dealing with here. These three equations that are given are just 3 planes and we're looking for where they meet. So what we're going to do is put a 3-dimensional plane, and these will be in your homework. There are many ways to do this. This is just the way I have been taught to do it. X, Y, and Z. We're going to use the rectangle method. So this says 2 in the X direction. So we're going to put 2 tick marks in the X direction like so. -2 in the Y direction. So I'm going to have to extend the Y backwards. And then 1 in the Z direction. That's going to be up. So let's say it's like right here. What you first do is make a rectangle on the X and Y. And notice how I'm trying to make it somewhat accurate. It should be slanted. So this line should be parallel to this line ideally. And then on the ZY axis, I'm going to extend this out like so. So now I can make a nice rectangle like that. So notice how I'm basically just making a 3D box. And the 3D box is going to illustrate where this point of intersection is. And I can see right here, that's my 3D point, 2, -2, 1. So right there. And you'll practice this in your homework.